Welcome to Unit 11, Section 3, the Fundamental Theorem of Calculus. In this section, we're going to look at the fundamental theorem and how it reveals a connection between two basic parts of calculus, both integration and differentiation. Now, the theorem itself has two main pieces, and even though those pieces are closely related, we're going to treat those two pieces separately and dig into how we're going to use them and what they're going to do for us. And in fact, we're only going to look at the first piece of the theorem in this unit, and then we're going to pick up the next unit with the second piece of the fundamental theorem. So let's first look at one of the rules that we had of integrating from 0 to some constant a of, say, the function x squared with respect to x. And we said that, well, this is simply just evaluating the antiderivative of x squared at a. And so we could say that it's big F, our antiderivative of a, or simply a cubed over 3. And we applied that to look at the definite integral. Say we wanted to go from 3 to 5 of x squared with respect to x. Then we would just evaluate the antiderivative at 5, and we would evaluate the antiderivative at 3, looking at the integral from 0 to 5 of x squared dx, and then subtracting the integral from 0 to 3 of x squared dx. And what this did was it showed us a way to evaluate the definite integral without having to use geometry, and it gave us this unique solution of just the difference between the antiderivative. And this actually isn't a coincidence, and this really is the essence of the fundamental theorem. And so the fundamental theorem states that if we have a continuous function f on the interval a, b, and big F of x is an antiderivative of f on that interval, then the integral of f of x with respect to x on the interval from a to b is simply the difference of the antiderivative evaluated at the endpoints b and a. And so this opens the door for us to be able to evaluate any definite integral using the antiderivative. So it connects the two ideas of integration and differentiation and melds them into one theorem here, and it helps us to essentially solve any definite integral that we want. Now, before we get into it, we need to talk a little bit about notation. And one little notation thing that we have here, if we're talking about the integral from a to b of f of x dx, and we want to evaluate the antiderivative big F, well, we use this notation here of f of x, and we have a bar, and we evaluate it from a to b right here. Okay, so we're going to use that notation just to shorten not having to have to write f of b minus f of a. Okay, so let's take a look at one here. So let's just have a simple integral of x cubed dx, and we want to integrate this from, let's say, 3 to 5. Okay, so to integrate this, what the fundamental theorem tells us is that this is going to equal the antiderivative evaluated at 5 minus the antiderivative evaluated at 3. Well, what is the antiderivative of x cubed? Well, the antiderivative f of x is going to be x to the 4th over 4. So we want to evaluate f from 3 to 5, and so we plug that in and we get 5 to the 4th over 4 minus 3 to the 4th over 4, and that gives us 136. And where do we get 136? Well, 5 to the 4th is 625, so we have 625 fourths, and then 81 fourths, and we subtract that to get 544 fourths, which is 136. So the value of this integral, the value of the integral of x cubed with respect to x over the interval 3 to 5 is 136. So we've found the area under the curve, we've evaluated the definite integral without having to use any geometry, only relying on the antiderivative. So you may have the question, now wait a minute, antiderivatives aren't unique. We were told when we first learned about antiderivatives that for any given function, we could have an infinite number of antiderivatives. So how do we know which one to pick? Because yes, x to the 4th over 4 is an antiderivative of x cubed, but so is x to the 4th over 4 plus 8, or x to the 4th over 4 minus 19. So there's many other antiderivatives we could use. How do we know which one to use? Well, in actuality, any of them work. It doesn't matter, because how do antiderivatives differ? Well, they only differ by a constant. So we know the true antiderivative of any function f of x is going to be big F of x plus some constant c. Well, if we evaluate this entire function from a to b, well, that gives us f of b plus c, that constant, whatever it may be, minus f of a plus that same constant c. And we notice when we subtract, these constants cancel out, and so we still are left with f of b minus f of a. So it really doesn't matter what antiderivative we use. So the easiest one to use is the one that has a constant of 0. Okay, so let's take a look at another one here. Let's say we want to integrate secant squared of x with respect to x from negative pi over 4 to pi over 4. Now, if we want to look at this graphically, if we just quick little sketch here, at 1, secant squared is going to look something like this, and we're going from right here at negative pi over 4 and right here at pi over 4. And so we're looking at this area underneath here. Now, looking at that area, that is not a nice shape. It's not something that we could use geometry to find. Okay, so we can't use those rules that we used with the antiderivative a few days ago. So because this isn't just a nice polynomial of x, it's a trig function. Well, now with the fundamental theorem, we can attack a problem like this, because this simply is going to equal our antiderivative evaluated at pi over 4 minus our antiderivative evaluated at a negative pi over 4. Well, we have to ask ourselves, what is the antiderivative of secant squared? So resort back to those 6 trig rules that I gave you, and the integral of secant squared of x is simply tangent of x. So our antiderivative is tangent of x, and you could say, well, don't forget the plus c, but let's just assume c is 0 to make our antiderivative a little more simple and easier to work with. So our integral here is simply going to equal our antiderivative evaluated at pi over 4 minus our antiderivative evaluated at negative pi over 4. So what is tangent of pi over 4 minus tangent of negative pi over 4? Well, we know tangent of pi over 4 is 1, and then tangent of negative pi over 4 is a negative 1, so this gives us 2. So the integral of secant squared x with respect to x between negative pi over 4 and pi over 4 is 2. So the area underneath this curve here that we're finding right there is in fact 2. Okay, so what this does, the fundamental theorem, and at least the first part of the fundamental theorem, remember there is a second part that we're going to learn later, but this first part allows us to evaluate any definite integral by simply finding the antiderivative and evaluating the antiderivative at each endpoint and finding the difference.